Force and motion, Unit 7 momentum, tutorial presentation.
Hello everyone and welcome to our presentation on momentum. My name is Aidan and I will be joined by Goodman Bing. We will excited to share with you what momentum is, how it relates to impulses, and why it's important in physics and daily life. Let's get started. So, here is our roadmap from today's presentations. First, we will define momentum and look at its fundamental concepts. Next, we will explore what impulses is and how it relates to momentum. After that, we will go through the principle or conservation of momentum and talk about different terms or correlations. We will show some example calculations from elastic, inelastic, and perfectly inelastic correlations. Then we will see how momentum apply to real-world situations. Finally, we will wrap up with good discussions, practice problems, assimilate, and exchange results. So, what is momentum? Momentum is essentially the quantity of motion an object has. We calculate it by multiplying the mass of the objects by its velocities. It's important to note that the momentum is a vector, meaning it has both a magnitude, how big, and a direction. The typical units are kilogram times meter per second. As an example, if you compare a slow-moving charge to a fast moving by circles, you can see how a higher mass or higher velocity can both result in larger momentum. What is momentum importance? Momentum is crucial from analyzing motion in physics. It tells us how an object will respond to force, especially in collision or impact. It's also key to designing safety features like airbags, since we want to manage how fast an object or a person decelerates. In sports, understanding momentum can impose tragedies. For instance, a player can use momentum to transfer maximum force to a basketball or a ball. Impulses is the change in momentum. If an object momentum changes, the change is directly related to the force applied and the time interval over which it acts. In simple, we say impulses equal force times the time interval. G equals F delta delta T. It also equals the change in momentum. Delta P, this means applying a big force briefly can have the same effect as applying a moderate force over a longer period, as long as the total impulses is the same.
We see impulse in action all around us. When a baseball player hits a ball that quick, powerful swing changes the ball's momentum in a fraction of a second. In a car accident, airbags deployed to extend the collision time of passengers, reducing the force on their bodies. Anytime a force is acting over a specific time, we have an impulse altering momentum. Sometimes we will present impulse with a force time graph. The area under the curve in a force vs time plot represents the total impulse. A higher area under the curve means a bigger impulse, hence a larger change in the object momentum. One of the most powerful principles in physics is the law of conservation of momentum. In a co-system where no external net force acts, the total momentum before any interaction is equal to the total momentum afterward. We will see how this principle helps explain the outcome of collisions, explosion, and even rocket launch. There are three main types of collisions. Large collisions, where both momentum and kinetic energy remain constant. Elastic collision, where momentum is conserved but some kinetic energy gets converted into other forms like heat or sound. Perfectly elastic collisions, where the objects stick together after colliding. In real world, most collisions are elastic to some degrees, but a dualistic collision provides a helpful model.
Now, let's identify the collision type in each scenario. First, two billboard balls colliding and bouncing off nearly perfectly. This is typically considered elastic. Second, a car crash will crumple metal. This is inelastic because kinetic energy is lost to deformation and heat. Third, clay dropping to the floor and sticking. This is perfectly inelastic. This quick check helps us understand how momentum and kinetic energy behave differently in each type. Now is the elastic collision example. Let's imagine two identical billboard balls. One moves at velocity v and collides head-on with another that's stationary. Because both momentum and kinetic energy are conserved, we can show mathematically that the moving ball transfers its velocity to the initially stationary ball and then comes to rest. This is a classic demonstration of perfectly elastic collision between objects of equal mass. Now is the inelastic collision example. Now consider a car of mass m1 and velocity v1 colliding with a stationary truck of mass m2. After the collision, they move apart with some final velocities v1 and v2. Momentum before collision n1 v1 must equal the total momentum afterward m1 v1 plus m2 v2. However, kinetic energy is not entirely conserved. Some is lost to heat, sound, or deformation. Now is the perfectly inelastic collision example. In a perfectly inelastic collision, the two objects stick together and move as a single mass. Using our car-truck scenario, if they stick together after impact, their final velocity is given by v equals to m1 v1 divided m1 plus m2. Since they move together, there's only one final velocity. Again, momentum is conserved, but kinetic energy is partly converted into other forms. Now is the momentum in rocket propulsion. Rocket propulsion provides an exciting real-world application of momentum conservation. As the rocket expels gases backward at high speed, the rocket itself is pushed forward. This process explains why rockets can accelerate in space, where there is no air. It's all about pushing mass one way to gain momentum in the opposite direction. Next is the momentum in the sports. Momentum plays a vital role in many sports. For example, in baseball, pitchers generate a lot of momentum during their wind-up, transferring it to the ball. In basketball, collisions under the rim can be understood in terms of momentum exchange. In soccer, a well-timed kick imparts a large impulse, sending the ball flying downward. Understanding these principles can help optimize performance. And then is the vehicle safety design. In the car design, engineers manage impulses to protect passengers. Seatbelts, bombas, and crumple zones are designed to prolong the collision time and throughout the force. Airbags also extend the time over with the passenger's body decelerates, reducing the peak force experienced. These by modern cars are far safer than older models. Next is the common misconceptions. Let's clear up a few misunderstandings. 1. A large mass does not necessarily guarantee a large momentum. Velocity matters. 2. Second, momentum is not the same as force. Force changes momentum, but they are not equal. And the last one is, momentum does not vanish a collision. Whatever decreases in one object is gained by another or by the environment, as long as the system is closed. Next is the impulse and collision recap. Remember, impulse is equal to the change in momentum. The idea behind airbags or safety nets is to increase the collision time so that the force is reduced for a given change in momentum. Likewise, large sudden forces can quickly change momentum, like a bat striking a basketball. And next is the lab demo proposal. For hands-on learning, we can propose a spring-load kart experiment. You can place two cars on a smooth track, compress a spring between them, and let them fly apart while measuring their speed.
We're going to do a mini collection simulation in goods. Use small ball, toy cars, or any material you find. Take quick measurements of mass and speed, or at least related speeds. Calculate total momentum before and after a collection. The goal is to see if you can demonstrate conservation of momentum right here in cars. Here are a few questions to get your mind working. Why do electric force on drag and speed challenge when dealing with momentum? How to seat belts and airbags reduce the safety of injuries? What new safety ideas could you imagine based on impulses and momentum concepts? Take a few moments to brainstorm in small group, and then we'll share responses. Let's do a brief quiz. So, we check the answers. 1. Their answer is object A. 2 is impulses equal the change in momentum, delta P. 3 is stay constant. It is conserved. Let's repeat again. The answer in the chess quiz is number 1 is object A. Number 2, impulses equal the change in momentum delta P. Question number 3 is stays constant. Is conserved. From those looking for more challenging problems, drive the final velocity of two objects that stick together with low external force. And if a 0.2 kg basketball comes in at 40 velocities and lift and 15 velocity in the opposite directions within 0.02 seconds. What is the efficacious force? Try working slow in your load or as homework. Remember, show off the stiff. To learn more, check out this reference. Okay, if you are really excited about momentum, you may explore angular momentum from water tank object or how collision work in complex non-linear systems. This can lead to cost-destructive results like biomechanics, where results inform how Atlantis use angular momentum or Oswald physics, which examines orbital dynamics. There are 3 questions over a rise. You can try to do it. So in the first questions, does momentum even truly disappear? No. It only seems to freelance if we don't consider the entire system. Okay, so we can trace in the second questions. Why do speed change so drastically post collisions? Because mass, velocity, collision angles, and energy conservation all play a role. So in the next questions, are perfectly elastic collisions real? They are mostly idealized. In everyday life, collision usually lose some energy to sun, heat, or deforming agents. Okay, let's recap the main point. Momentum is mass times velocities, P equal to mv. Impulses is the product of force and times, which equal the change in momentum. G equal to F delta T equal to delta P. Momentum is conserved in a closed system, so total momentum before and after a collision remain the same. Real-world applications appear in sport car safety and walker trials. We also see how collision can be inelastic or perfectly inelastic, affecting kinetic energy differently. So, thank you for following along our journey into momentum. Feel free to ask questions or share observations. If you'd like to know more, please get in touch. We appreciate your attention, and now we'll open up some questions.